Today I am going to discuss change of melting points of D block elements, especially 3D block elements. Let's see which elements are 3D block elements. Scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. These are the elements known as 3D block elements. As these elements belong to the same period, that is fourth period, these elements melting point and boiling point are supposed to change gradually. Change of melting and boiling points of these elements should not be unusual, but their melting and boiling points change abruptly. Let's see melting points of these elements. Scandium melting point is 1541 degrees Celsius. For titanium, this is 1660 degrees Celsius. Vanadium 1890 degrees Celsius. For chromium, this is 1857 degrees Celsius. For manganese, this is 1244 degrees Celsius. For iron, this is 1535 degrees Celsius. For cobalt, 1495 degrees Celsius. For nickel, this is 1453 degrees Celsius. Melting point of copper is 1083 degrees Celsius, and for zinc this is only 420 degrees Celsius. That is, melting points of these elements changes like this. Scandium to titanium, it increases. Titanium to vanadium, it increases. Vanadium to chromium, it decreases. Chromium to manganese decreases a lot. Manganese to iron, melting point increases again. From iron to cobalt, it decreases. Cobalt to nickel, melting point decreases. Nickel to copper decreases. Copper to zinc, melting point decreases. That is, change of melting points is unusual. Abrupt change occurs. But change of melting points and boiling points of these elements should be gradual change. But not gradual change, abrupt change of melting point and boiling point occurs. What is the reason behind this? This is today's lesson. So let's go to the detail. First point is metallic bond and melting points of sodium, magnesium and aluminum. Let's look at the matter. First of all, let's see. Suppose this is metallic piece of sodium. These are the sodium atoms. Electronic configuration of sodium is 1s2, 2s2, 2p6, 3s1. Sodium contains only one electron in its outermost shell. In the piece of sodium metal, all the sodium atoms donate one electron each, and sodium atoms turn into unipositive charge ions like this, because here all the atoms donated one electron from its outermost shell, and this electron remains among the positively charged ions. So here electrons remain among positively charged ions. That means if we consider two ions, positive charge sodium ions, then we see at the middle negatively charged electrons. That is, here electrons act as gum among positively charged ions. That is, because of these movable electrons, atoms or ions are connected by attraction force. That is, negatively charged electron and two positively charged ions. So there is an attraction force here. This attraction force is called metallic bond. In case of sodium metal, only one electron participates in metallic bond formation. So among the positively charged ions, concentration of electron is less. That is why metallic bond is here weaker, and for this reason sodium is soft metal and its melting point is comparatively lower. Its melting point is 97.79 degree Celsius. Another metal, magnesium, from the same period, suppose this is piece of magnesium metal, these are the atoms. Electronic configuration of magnesium is 1s2, 2s2, 2p6, 3s2, total 12 electrons. In case of magnesium, we see that in the outermost shell of magnesium there are 2 electrons. For sodium it was 1 electron, for magnesium 2 electrons. So all the magnesium atoms donate 2 electrons each, and these atoms change to di-positive charge ion, 2 plus, 2 plus, 2 plus, like this. And electrons from each atom act as gum among the di-positive ion, magnesium ion. So here concentration of electron is higher compared to sodium. That is why in case of magnesium, metallic bond is stronger compared to sodium. That is why melting point of magnesium is 650 degree Celsius, because here from each magnesium atom 2 electrons participate in metallic bond formation. Let's see about aluminum. Suppose this is aluminum metal. These are the atoms of aluminum. Electronic configuration of aluminum is 1s2, 2s2, 2p6, 3s2 and 3p1, 13 electrons. In case of aluminum, in the outermost shell of aluminum there are 3 electrons. All these 3 electrons from each atom participate in metallic bond formation in this way, and all the atoms change to tri-positive charge ions, 3 plus, 3 plus, like this. So here concentration of electrons is higher than sodium and then magnesium. So in case of aluminum, metallic bond becomes stronger. Here aluminum atoms are connected with strong force compared to sodium and magnesium. That is why melting point of aluminum is 660 degree Celsius. We see that sodium, magnesium and aluminum that belong to the same period, third period. That is why their melting points change gradually 97.79 to 650, 650 to 660. This is normal trend of changing melting points of the same period elements. But in case of D block elements, especially 3D block elements, change of melting points is abrupt, unusual. This is actually today's point to be discussed. Let's move on to the main point. Melting point and boiling point mainly depend on these factors: number of unpaired electrons in the outermost shell, total number of electrons in the outermost shell, and then electronic configuration in the outermost shell. That is, whether the configuration is stable or unstable. Let's see melting points of 3D block elements according to their electronic configurations. Scandium 21, outermost electronic configuration is 3D1 4s2. Here, energy difference between 3D and 4s is extremely little. That is why 3D electron and 4s electrons participate in metallic bond formation. So here, total 3 electrons participate in metallic bond formation. That is why melting point of scandium is very high, that is 1541 degrees Celsius. Then titanium 22, electronic configuration is 3D2 4s2. Vanadium, chromium, manganese, iron, cobalt. Vanadium 23, 3D3 4s2. Chromium 24, 3D5 4s1. It is rearranged to get stable electronic configuration. That means now both the orbitals are half-filled, which are stable orbitals. 25, 3D5 4s2. Iron 26, 3D6 4s2. Cobalt 27, 3D7 4s2. If we see box system, then we see 3D 1 2 3 4 5, and this is 4s. Here 1 2 3 4 5 4s. 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 Here d orbital contains 1 electron, s orbital contains 2 electrons. In case of scandium, only 1 unpaired electron is present here. Here, number of unpaired electrons in the outermost shell that gets priority to know the melting point of elements. In case of titanium, 2 unpaired electrons. Here 2 electrons. That is why melting point of titanium increases from scandium, that is 1541 to 1660. In case of vanadium, 1 2 3 4 5 4s, 3 unpaired electrons and 2 electrons here remain as paired. So in case of vanadium, we see number of unpaired electrons increases. That is why melting point increases from scandium to titanium, titanium to vanadium. Titanium 1660, for vanadium 1890 degrees Celsius. Let's see for chromium. Here 5 electrons in d orbitals, 1 2 3 4 5, and 4s orbital contains 1 electron. Here we see that d orbitals and s orbital contain 1 electron each. That is, this is symmetrical configuration, which is considered stable configuration. That is why these electrons cannot participate in metallic bond formation properly. That is why here for chromium metallic bond becomes weaker. That is why melting point from vanadium to chromium, it decreases. Vanadium 1890 degrees Celsius, for chromium this is 1857 degrees Celsius. Now let's see for manganese. D orbitals contain 1 electron each and s orbital with 2 electrons, that is completely filled. So this electronic configuration and this electronic configuration of manganese is more stable than electronic configuration of chromium. Here one orbital is completely filled and another orbital is half filled. That is why this is more stable. For this reason, melting point of manganese decreases from chromium. Chromium's melting point is 1857 degrees Celsius, but manganese melting point is 1244 degrees Celsius, because this electronic configuration is more stable. These electrons are not willing to form metallic bond. That is why metallic bond here becomes weaker. Now let's see iron. Here d orbitals contain 6 electrons, 1 2 3 4 5 6. S orbital contains 2 electrons. That is, here number of unpaired electrons is more, but this is not stable configuration. This is fulfilled stable, this is not half filled, not fulfilled. So this is unstable electronic configuration. That is why these electrons participate in metallic bond formation. For this reason, melting point increases from manganese to iron. Manganese melting point is 1244 degrees Celsius, but melting point of iron is 1535 degrees Celsius. Now let's see about cobalt. D orbitals contain 7 electrons, 1 2 3 4 5 6 7. Here 2 electrons. In this case, number of unpaired electrons decreases from iron. That is why melting point decreases for cobalt from iron. Iron's melting point is 1535 degrees Celsius, but cobalt's melting point is 1495 degrees Celsius, because here number of unpaired electrons decreases. That gets priority to get melting point. So because of the less number of unpaired electrons for cobalt, melting point decreases for cobalt from iron. Now let's see about nickel. Nickel atomic number is 28. Electronic configuration is 3d8 4s2. Then copper 29. 3D10 4s1. Electronic configuration is rearranged to get stable electronic configuration. That is, this is full filled, this is half filled, which is stable electronic configuration. Now zinc 30 3D10 4s2. Let's write box system 1 2 3 4 5 and s orbital. Here 1 2 3 4 5 s orbital, 1 2 3 4 5 s orbital. 3d orbitals contain 8 electrons, 1 2 3 4 5 6 7 8. Here 2 electrons. In case of nickel, number of unpaired electrons decreases more than cobalt. So melting point of nickel decreases from cobalt. Cobalt's melting point is 1495 degrees Celsius, but nickel's melting point is 1453 degrees Celsius, because in case of nickel, number of unpaired electrons decreases. Now let's see about copper. 10 electrons, 1 2 3 4 5 6 7 8 9 10. Here 1 electron. In case of copper, this is full filled orbital and this is half filled orbital. So it's a stable electronic configuration. Because of its stable electronic configuration, these electrons are not willing to make covalent bond. That is why in case of copper, metallic bond becomes weaker, and that is why melting point of copper is 1083 degrees Celsius, which decreases from nickel 1453 degrees Celsius. Now let's see about zinc. Zinc's melting point is only 420 degrees Celsius. Why? Let's see. Zinc 30, that is d orbital is fulfilled, 10 electrons. S orbital 2 electrons. That is d orbital and s orbital. Both the orbitals are completely filled with electrons, which is very much stable electronic configuration. That is why in case of zinc, metallic bond becomes weakest. For this reason, melting point of zinc is only 420 degrees Celsius. So let's summarize the reason behind the changing of melting points of 3D block elements. That is, number of unpaired electrons, total number of electrons, and then electronic configuration in the outermost shell, whether this is stable or unstable. Let's see a graph of melting points of these elements. Here atomic number, and this is melting point. Scandium, then vanadium, it increases, chromium increases, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. That is, here scandium, titanium, vanadium, chromium, manganese. Manganese melting point is decreased a lot. Manganese, which is stable electronic configuration, full filled and half filled orbitals. Again, melting point of zinc is lowest, because zinc's electronic configuration, if we see, this is stable electronic configuration. That is, here we see that melting points increases, then decreases, again increased, again it decreases. This is the pattern of change of melting points of 3D block elements. The reason is outermost shell number of unpaired electrons, total number of electrons, and electronic configuration. This is all about change of melting points of 3D block elements. No more today. Thank you very much.